ahead and get started. Okay, so this week we are doing mainly chirality and enantiomers. But before we do that, we are recording these lectures, so when you signed in, you should have gotten a consent form. You had to put in yes, your net ID. We are recording these lectures, and you can actually access last week's lecture online. So there's a QR code. I don't know if it works. Can someone check if it works? I hope it does. It should take you to a YouTube thing.
Yeah.
It does?
Mm-hmm.
How do you scan it?
Okay, so if you have an iPhone, just open your camera app, and it should automatically suggest that there's a link.
Just a camera?
Yeah, just open your camera app, and it
Yeah, I know.
does it work?
Interesting.
Yeah, it works.
Okay, cool. So we're recording these lectures. So if you don't want us publishing your grades, don't talk about your grades because it's getting recorded. So life pro tip. But we're recording them, and hopefully we'll upload this lecture soon-ish, provided everything goes well. So last week's is on. We don't have the first 2 weeks because we were still figuring out all the technology. But hopefully we're at a place where this is a little easier. No, I don't want to touch. Okay, perfect. So let's go ahead and start. First thing we did was RNS configuration. Y'all remember what that is? Yes?
Yes.
Yes. Yes. I'm not giving yeses. Okay, cool. All right, so in order for us to do RNS configuration, we have to start with knowing what is R, what is S, and why we do it. So when do we do RNS configurations? When is a good time? What is the only type of carbon I can put RNS configuration on? On a chiral carbon. So this must be chiral. And what does it mean to be chiral?
4 different substances.
Yes, must be 4 different things. So RNS just basically mean the chirality direction. So R means right, so I'm going to go to my right. S means left. So cool fact, this comes from Latin. The S back then in Latin, S, the root word for left in Latin is the same word that we have for sinister. So people thought that left-handed people were of not good repute. And so S back then was left. And that's how we get the word sinister. Okay, so for this structure, structure A, let's go ahead and dive in. Let's talk about chiral carbons. So, do we have a chiral carbon on this structure? Yes?
Yeah.
All right, which carbon is chiral? Or do we have more than one?
We have OH
And
CH3 and N carbon.
This one?
Yeah.
Yes.
Okay, so this is a chiral carbon. Do I have any other chiral carbons?
Yes.
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 Okay, which one?
Which has the propyl.
This one?
Yes.
Is this chiral?
One carbon.
This one?
No. No.
Yes or no?
No.
Okay, how do I know if this is chiral or not? How do I know if a carbon is chiral or not? So I know that a chiral carbon has 4 different things. So does this carbon, carbon 2, have 4 different things? No. Why not? What are the 2 things that make it same?
There's 2 ethyls.
I have 2 ethyl groups. Because the ethyls are the same, they are different. Because they are the same, it is not chiral. So this is not chiral. Okay. How about this carbon? Do I know this is chiral or not chiral? It's not chiral. Why not? Because because I have 2 hydrogens, right?
Yeah.
And that automatically says it doesn't have 4 things. How about this carbon? Is that chiral? No, why not?
3 hydrogens.
I have 3 hydrogens, right? So automatically you can know if something's chiral or not based on the 4-thing rule. So if I have 4 distinct things, then it is chiral. If I don't, then it is not. So these are not chiral. Listen for unique things. Okay, but we do have one chiral carbon, and I'm going to make that one blue. Okay, so blue carbon. So the first thing we want to do is we want to make sure that our least numbered thing is facing away from us, or we can do something else. So let's do it the first way, and then we can rotate it and see if it works. Okay, so the way I usually do it is I go ahead and start numbering, right? Because I need a number in terms of most priority to least priority. So my 4 substituents, what is going to be my highest priority substituent? Bromine? Anybody agree, disagree?
So to find out the higher, do we like look the atomic mass or something?
Yes, the highest atomic number makes it the highest priority. That is Kahn, Engel, Prelog. And you guys can find more about that in your lecture notes. But there's a bunch of rules. We'll go through those rules. But yes, the higher the atomic number, the better. Higher atomic number is higher priority. Okay? So bromine is 1. Okay? So what is my second priority? My alcohol, yes, so this is 2. And so when I'm looking at 3 and 4, I have 2 carbons. So I'm not going to be comparing carbons because they have the same atomic number. What I'm going to do is I'm going to continue looking at the next thing I'm attached to until I get something different. So I have this carbon, and this carbon is attached to a hydrogen, right? If I look at this carbon, it is attached to a carbon, and because a carbon is a higher priority than a hydrogen, this one wins 3, 4. Does that make sense? Okay, so now I'm going to just go, and what I'm going to do is I'm going to like draw a little circle based on the way that things are oriented. However, when I do this, I want to make sure that my lowest priority is facing away from me. So right now, is my lowest priority facing away from me? No, it is facing towards me, right? My lowest priority is 4, and it's on a wedge, which means it's facing towards me. So I have 2 options. If my lowest priority is on a wedge, I can draw the circle, label, and then change it. Or I can rotate. I can do 2 things. So let me show you guys how that works. So right now I can do it. I'm going to go this way. What is that?
S.
S. But because the 4 is facing towards me, I switch it to R. Basically what I'm saying is I rotate it, and then I'm looking at it from the other side. So I switch it. And this works because let me draw it the other way, okay? So I have this. I'm going to call this, and then I'm going to call this group, just G, okay? And I'm going to rotate this so that the wedge is currently on a dash. So I'm going to do this, my CH3. When I do that, the alcohol becomes facing towards me. And then no, it doesn't. No, my bromine becomes in the page. And my alcohol faces towards me. 1, 2, 3, 4. And you see how I still get S. Hold on. 1. No, wait, sorry. Yeah. Okay. 1, 2, 3, 4. And what do I get? R. So, if my least priority is facing towards me, I can do it normally and swap letters or rotate. And both of them will get me the same answer. Does it make sense? Okay. Note if it is if it's in the page, this trick doesn't work. Okay? So if my least priority was in the page, I would have to rotate to get the least priority into the page or away from me. Questions about how this works, RNS configuration?
One more time. You said if it's in the page, you have
Okay.
to.
So in the page means like here.
Mhm.
If it's in the page, I cannot use this trick. I have to rotate. This
Okay.
only works if the least priority is facing out of the page towards me. Okay? Out of the page towards me, I can do it normally and switch or rotate. Either one works.
Okay.
I like this way because it's a little faster. Every time you rotate, you introduce a risk of getting it wrong. For example, just like what I did. Questions, comments? How are we feeling about RNS? Something good, not good? Okay, cool. So there's 3 questions here. What I'm going to do is I'm going to move on to the next type of question. So I'm going to move on to question 2. I'm going to save B and C and we'll do it later when we have time. So let's keep going and then let's move on. So we'll do B and C later if we have time. Let's go on to number 2. And that is enantiomers. So what is an enantiomer?
Is that the mirror image?
Yes. So all I need to do is make a non-superimposable mirror image. So what I like to do is I like to draw a line across, and I just draw the exact same thing, but like flipped. So I get my cyclohexane, and then on this carbon, I get the same thing. Now here's a question. Do I get an enantiomer when I do this? Is this the same thing as this?
Yes.
This is just
Yes, this is same thing, not an enantiomer. Okay, so just be careful of that. Sometimes you'll get, when you make your enantiomer, you'll get the same thing and you don't get an enantiomer. This is an example of how you can flip it and not get an enantiomer. So for example, if I were to do the next one, this
Okay,
one,
I have a question, I'm
yes,
sorry.
yes.
Okay, enantiomer and same thing, okay. So same thing is literally,
This is literally the same thing. I can rotate the chlorine and I will literally get the same thing. Do you see how if I rotated this a little bit, I'd literally get the same thing?
so how would that have been an enantiomer?
So for example, if I were to get the enantiomer of this, am I getting the same thing?
That's the same.
If I were, yes, but it's an enantiomer. You see how I took a mirror image of it? Sometimes when you take an enantiomer, you'll get the same thing. That's what I'm trying to point out. So you just need to be careful. So sometimes how they used to do it on a test was they would have a list of just a bunch of structures and say, is this the same thing? Is this an enantiomer? Is this all the different types of things you can get? So this looks like an enantiomer, but is it an enantiomer?
So for a mirror image, is it switched like left and right? Like this one is left and right and this one is right and left? Like how you look in the mirror?
Yes, it's literally like if you were to look in a mirror. So it's reflected image. You see how this is a reflected image, but I literally did the same thing. Yes. Okay, so let me do the next one and this will make a little more sense. So on the next one, I'm going to also do an enantiomer. Start with a cyclohexane. All right. No, come on. Whoa. So we get our fluorine, get my ethyl. All right. No, I did this wrong. Oops. Okay, so now I have an enantiomer. Do I have the same thing?
No.
No, because if I move this over, my ethyl is going to be on the other side. So do you guys see how I didn't get the same thing when I took the enantiomer of this one?
Okay.
Sometimes when I take an enantiomer, I'll get the exact same thing. Sometimes I won't. So it's important to be careful when you do this to make sure you don't get to check, right? So this one, literally, all the enantiomers are going to be the same thing. So sometimes you can't get an enantiomer of something. That's what I'm trying to say. You can't get an enantiomer. In this case, you can't. In this case, you can. So just be careful, because on a test they'll try to trick you with questions like
So
this.
you mean that we couldn't move the fluorine and iodine, like it's in the same plane? That's what you meant, that it cannot be an enantiomer?
No, this is an enantiomer.
This is.
This is a enantiomer. This is. The other one is not.
Oh.
So mirror image, not an enantiomer. Mirror image is an enantiomer. It just depends.
So this is like the process to get an enantiomer, and then you decide after doing that if it is or not?
Yeah, because sometimes they'll trick you and tell you to take a mirror image, and it turns out to be the same thing, not an enantiomer. Because an enantiomer is a non-superimposable mirror image. Non-superimposable. So just because it's a mirror image doesn't mean it's an enantiomer. So just be careful about that. Okay, so how do y'all feel about chairs? I included cyclohexanes so we can practice chairs. Do y'all want to do chairs? Do y'all not want to do chairs? Because we do chairs. But
Yeah, just a chair.
all right, let's do a chair just for fun. Okay, cool. So I have this structure. People who were here last week will know the EA trick. People who were not here last week, do y'all understand the EA trick? Or do y'all know what that is?
The EA trick?
I'm going to show y'all, and then we'll go with it.
The
Okay.
axial equatorial one?
Yeah. So what I'm going to do is I'm going to go around the circle, and I'm going to assign equatorial or axial.
That, okay, yeah.
So E, A, E, A, E, A. If they are different from what I started with, I have to switch it. So I started with equatorial facing upwards, and I went around. So because this one is facing a different direction, I need to switch it. So I have 1 and 4. Go ahead and draw my chair. I'm going to call this 1. So on 1, I have equatorial chlorine. 1, 2, 3, 4. On 4, I have equatorial tert-butyl. Okay? Is this the most stable conformation for my chair?
Yes, because both are on equatorial.
Both of them are equatorial. So, a quick note, this is what we call a tert-butyl. And this is going to be always equatorial. So for example, if I had this and the chlorine was an axial, the tert-butyl will always force itself into the equatorial, even if it makes everything else unstable, because it's so big. Does that make sense?
Could you explain how you have axial equatorial? How do you know which carbon is axial, which carbon is equatorial?
What do you mean?
You know how you label the ring equatorial, axial?
Mhm.
So how do you know which one is axial?
I arbitrarily I know it alternates. It alternates assuming that I'm facing the same direction, okay? So if I had a ring where everything was facing the same direction, I could go E, A, E, A, E, A. If I have something facing a different direction, I'm going to cross it out and switch the lettering.
So you just blindly did EA around the ring?
Yes, but I draw the chair and I want to make sure it's the most stable conformation, right? So I have 2 alternatives, right? I could either do this or I could do this. A, E, A, E, A, E, right?
Okay.
It's only 1 or 2 options,
Okay.
right? And so there's certain things that I need to make sure are in the equatorial position. The biggest thing is always equatorial. So for example, right now, I have a tert-butyl. It has to be equatorial. I don't have to switch it because it's already in equatorial position. I want as many things in the equatorial position. I don't have to do anything here. I have all my things in equatorial position. So there's times we need to double check and make sure, but here it works. So we're just gonna go with that.
Okay.
Perfect. Any other questions? Sweet. Okay, so do you guys want to do the other chair or do y'all want to move on to RNS chirality and Fisher projections?
RNS chirality and Fisher.
All right, Fisher projections, my favorite. I'm kidding. I don't like them. Okay, but we have to do them. All right, so when we do Fisher projections, Fisher projections are basically the line through, and we do the little, oh, this is an ugly line. Okay, straight line. And then we do our little crosses. Okay, so when we do this, we want to make sure our most oxidized carbon is on top. So a COOH, do you all know what that stands for? Carboxylic acid, right? It's going to be this thing. So that gives me the most oxidized carbon. It is bonded to the most oxygens. So that's going to be on top.
Every time anything which is more oxidized would be on the top.
Yes, your most oxidized carbon is always on top. Okay? So COOH. And now what I'm going to do is on a Fisher projection, I have all the little crosses. All the ones that go across represent carbons. Okay? So I have 1, 2, 3, 4. 4 carbons that go across. Okay? I'm going to go ahead and number my carbons. That'll make life easier for all of us. So in red, I'm going to call this 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. And 6 is a CH3. I'm going to go ahead and draw that in. No. How do I undo? I don't think I can undo. Six. Make sense? Any questions about what I've done so far? Okay, so when I do Fisher projections, they are different from Newman's, right? In the sense that on my bar, I'm going to draw it assuming that everything faces me. Okay? Which means that, do you see how on one carbon it faces up and the other carbon it faces down? My little substituents. So it's going to be like wings, right? So on carbon 5, my substituents will look like this. On carbon 4, my substituents look like this. They're facing down, which means I have to change my perspective every single time. So if this were my eyeball, I'd be looking like this and like this. Okay? So if we're looking at it like this, my carbon is already here. So carbon 2, is it already facing me or not? I'm going to take it. This is much harder on a tablet. Okay, I'm going to take this. I'm going to rotate it. All right, rotate it. Is this carbon facing up or down already? When I rotate it, it kind of like. So currently it's in the page like this, right?
Yeah.
I'm going to do this
So it's
and then do this.
It's still pressing down.
It's going to be facing up.
Facing out, outside.
The bromine's going to be facing towards me, all right? Because currently it's in the page, right? Currently, think of this entire carbon chain as a piece of paper, okay? It's in the page. Now I'm going to rotate it. I'm going to rotate it up, okay? So now is the bromine facing towards me or into the page? When I rotate it like this.
It's coming out.
It's coming out, okay? And I rotate it like this. So now the bromine is coming out. Does it make sense?
Okay.
I know this is very hard to visualize.
Okay.
Fissures are the hardest thing to draw. Newmans are like easy peasy compared to this. So, does this make sense?
Okay.
Boom, boom.
Mhm.
Okay, so everyone agree bromine is facing towards me. Okay, so let me draw that real quick, okay? Well, I can't draw that, that's really hard to draw. But, yeah, so bromine is facing towards me,
Okay.
okay? When bromine is facing towards me, actually, I'm going to try to draw this. I'm going to try to draw this. This actually might make things easier. Okay. So I have COOH on top. I have 4 carbons. CH3 on the bottom. Okay. So when I rotated everything, the bromine was facing towards me, which means that they are now on wedges. Okay. That means on the next carbon, everything is on dashes. Carbon, wedges, dashes. No. Does this make sense? Every other carbon, I switch between wedges or dashes when they're facing towards me. Okay. So, as I look at this, is bromine on my right side or my left side? Bromine is on my right. Questions about how I got there?
So
Does that make
it's a wedge or it's a dash in the fissure?
In the fissure, right? A wedge or dash basically means in the
In the
page
page and
or
out.
out of the page, right? Currently, it's going into the page.
Mhm.
But when I rotated it,
It came out of the page.
it came out of the page, and now both substituents are facing towards me.
Yeah. Okay.
And now it's on my right side.
So it simply went from, I mean, technically a dash to a wedge.
It did not. Yes and no. Dash and wedge, literally the only thing it means,
It's in the page and out of the page.
yes. Yeah, that's the only thing it means.
But it went from in the page to out of the page.
Yes, but not in the traditional sense, right? We also move the page around.
Okay.
Do you see what I mean?
Yeah.
We're dealing with lots and lots of different planes here.
Okay.
We're dealing with the plane of the carbon-carbon change. We're dealing with the plane of the paper, right? So the paper didn't move, but the carbon moved, which is why it is now out of the page. We changed our entire perspective. Literally think of it as me, right? So I'm going to put this carbon on top. So it's basically me lying down here,
And now standing back.
and I'm looking at, which means bromine's on the left, not on the right.
Okay. So bromine's on the other
Bromine's on the
side.
left, yeah.
Okay.
Yeah, okay. See, look, because I'm basically like laying down, looking at it like this, okay? Don't do this on the test, but it's literally me
Yeah,
laying
yeah.
down and looking at it.
Yeah.
So, no, it is on the
See,
right. I'm
no,
so
That's
dumb.
what I'm about to say, since we moved it to out of the page. Like,
I'm so dumb, it's on the right. I'm so dumb. I was
It
like, no.
was on the left at first though, right? In the beginning.
Right? So if I look at it from the top, it's on my left.
Yeah.
But I'm looking at it from the bottom, which
Yeah.
puts it on my right.
Right. Okay. So it's on your right to begin with.
It's on my right.
It's been on your right for a long time. It's still
So-
your right now.
Yeah.
Yeah, it didn't move
It's
at
just-
all.
That's what I'm.
Yeah, it didn't move at all. It's still your
So
right.
is a fissure projection like a view from the bottom?
No, it's a view with the things, substituents facing towards me. So when I switch it, when I look at this carbon, when I look at carbon 3, the things are facing upwards, right?
Mhm.
So I need to change my perspective. On a fissure projection, I change my perspective every other carbon.
That is so weird.
It is very weird.
Like,
This was originally designed to do sugars, and so sugars are real long chains. So this is how we. This is why we don't eat sugar, guys.
Oh, stop now.
Okay.
Does this make? I know this is really weird, but is it any of it starting to like kind of make sense?
So
Yeah.
like with every carbon, we are changing the perspective. So for example, the bromine
I'm looking from the
was
bottom,
bottom to now the carbon's looking from the top.
top, bottom,
to
top. I alternate.
Okay.
Oh. Oh, okay, that's.
No. This isn't like some 360 thing. It's top or bottom
so-
alternating.
Because at the bromine, we started by looking at that from.
Think of it this way: the direction of this carbon pointy, the arrow, very technical terms here, right? The pointy is the direction I'm looking. So if it's point down, I look from the bottom. Point up, I look from the top.
Okay, okay.
Just look in the direction of the
So,
pointy.
even if the bromine started off on the top, we would we need to, we would keep it on outside the page, right? And then alternate the second one, the second carbon? Like, I'm thinking we're alternating the bromine because it's in the page and we want it out.
This has nothing to do with in or out of the page. I can have something else like this,
Mhm.
and it wouldn't change the way I'm doing this.
So it doesn't matter, we're gonna alternate it regardless of what.
Doesn't matter. In or out of the page does not matter,
Okay.
right? Because remember, these carbons have two things attached to them, right? On this carbon, I have 2 hydrogens. I have 1 in or out of the page. Doesn't matter. In or out of the page, I do the exact same thing. Everybody? All right. Let's work through this, and then hopefully it'll make a lot more sense. Okay, so I'm looking at it, and I've rotated everything. Currently, I'm looking at it from the perspective of the things pointing at me, which means I'm looking at it from the bottom.
Mhm.
When I look at it from the bottom, bromine is on my right, and I have a hydrogen on my left. Okay?
Okay, I'm sorry. I'm looking at it like this, right?
Yes.
And bromine is on the, is
Right.
it on the right because now we have alternated it?
No, we have not alternated
We
anything.
haven't done anything and it's, so, see, now I'm confused, why is it on the right if it was on that dash?
Because it's into the page. Right? Here's my sheet. This is my paper. My bromine is into the page. When I'm looking at it like this,
Yeah.
it's on my right.
Okay. All right.
Paper into the page, right side.
And out of the page is on the left.
Yes.
Okay.
Okay.
Questions about how I got the first carbon? Let's only talk about the first carbon.
So you start there because that's where the chirality.
Because,
You move in the direction of like where it starts at 1 and then you move that way.
yeah, so this is the top one, so I'm going to look with this one on top, which means I'm looking at it this way.
Okay.
Okay.
Questions? Alright, so the next carbon is going to be facing up. So now I'm going to look at it like this. Okay? Doesn't matter if they're two hydrogens, so it doesn't really matter for this one. I'm going to go ahead and draw them in. Hydrogen, okay. So I'm going to call this H1, H2. Okay. So I'm going to look at it from the top this time. I'm looking at it down, okay? I'm looking at it this way. Out of the page is going to be H1 or H2.
H.
Hold on, let me redraw that. It's really ugly. This is H1 and H2.
H2.
Right. I'm looking at it this way. I'm looking at it down, and this is my carbon chain. Okay? Now, on my right side is H1 or H2.
H1.
1 or 2.
The one out of the page is
The one
on this
that's-
side, right?
The one out of the page. Alright, so I'm looking at it this way. Right. Remember, look, the way I'm facing is different. When I was looking at the ones that are facing downwards, I was looking at it this way. Now I'm looking at it this way.
What made you turn that way? Why you?
Because I need to look at it with the carboxylic acid on top. Right? So it'll switch. Remember, I'm alternating my view every single time.
I thought you meant up and down, but now you
Yes,
mean.
up and down also means that my placement's going to be different, right?
Yeah.
When I'm facing, for example, if I'm lying down,
Yeah.
my right hand is going to be away from you,
Right.
right? When I'm lying face forward. When I'm lying face down, my hand's going to be on a different side.
Yeah.
Yes.
So, if I'm looking at it this way, from the bottom, my right hand's going to be on one side. When I'm looking this way, my right hand's going to be on the other side.
Right.
The same thing for this, okay? I'm going to look at my carbon chain. When I look at it from top, my right hand is going to be out. I'm looking from the bottom, my right hand is going to be in.
Yeah.
Okay. So, I'm looking at it from the top for carbon 3. Right? I'm looking from top. On my right is going to be H1 or H2. And it's going to be the one that's inside of the page or out of the page? Out of the page. Is that H1 or H2?
H2.
Dash is out of the page or into the page?
And
In the page. So if I want out of the page, what am I looking for?
H1.
The wedge, which is H1. Okay. Does it make sense?
almost.
So on my right will be H1, H2.
Because you said the dash is inside the page? Or is it
Dash
towards-
equals in / away. Wedge equals out / towards.
Okay.
Questions about carbon 3?
Not yet. Let's keep going.
I know this is really, really complicated, but hopefully this is making sense one by one. Alright, so let's move on to the next carbon, let's see. Okay, carbon 4. Which way am I going to be looking at it?
You're gonna be looking down.
I'm going to be looking at it from the bottom, right? So I'm going to look at it from the
You're
bottom.
gonna be looking up there.
I'm going to look up
Yeah.
from the bottom, right?
Mhm.
So, I have a methyl and a hydrogen. Let me draw in my hydrogen. That'll be helpful. Okay, so looking at it this way, my hydrogen, is it on my right or my left?
Your left.
My left. Why is it on my left?
Because it's out of the.
Out of the page, and because I'm looking from the bottom. All right, perfect. All right, so the hydrogen is going to be on my left, and then that means my methyl must be on my right, right? Because I'm looking at it like this. Hydrogen is on my right. Okay, and let's move on to carbon 5, last carbon. I'm going to draw my hydrogen. Okay, so carbon 5, I'm looking this way from the top.
So you're looking down.
I'm looking down.
Okay.
Okay? Hydrogen on my right or my left?
Your left.
Left or right?
It's on the left.
OH will be right.
Right.
OH will be right, alcohol will be right, hydrogen will be left.
Right.
Alcohol is right, hydrogen left.
So the left, right, looking at it, is it after you flip that? I mean, after is like, I guess, straight, or you looking at it in this way? You know, because for the BR, you said we have to move it upward. We have to flip it. Us, I guess.
Yeah. So there's two ways of thinking about it. What I can do is I can rotate all of them,
Yeah.
or I can just change my perspective. There are two ways of doing it. Both of them are perfectly valid.
Okay.
The way I've been doing up here has been changing my perspective. It's a little easier to understand because like doing the mental flipping trick is a lot of work. So just imagine the paper and like, don't do it all the time. Don't like lie on the floor, that's weird. But, but right, do you guys think you guys can practice at the point where you can like visualize I'm looking at it this way, I'm looking at it that way?
I'm trying to. I can see the in and out. I can see the, I guess, out or whatever.
Okay, so
I'm looking at it that way.
So I'm looking at my paper. This is my paper, right?
Mhm.
Okay. So my COH is going to be on top, which means it's facing this way. And then I'm going to look at it like this, right? And I'm going to pretend I'm looking at it from the bottom. Like this,
Okay.
all right? So this way, because it's into the page, it's like this. Because it's into the page, the bromine is going to be on my right.
That's it.
So
Okay.
I think, I don't know if I can.
Okay,
so
go ahead.
What I understand is that, for example, if we are in carbon 5, so we are standing here, and then you see that it's the wedge. So wedge means outward, and the right hand is outward. So that's OH, and you see the dash means like inwards, and by this side the inward is our left. So that's why we put the edge then on left.
Okay.
Okay, makes sense. Little bit.
That kind of makes sense.
Okay.
Okay.
Maybe a little more sense. Here's the thing, I'm looking at it from a projector, so this all like makes
Oh no.
sense to me. I'll have done it for a while. But does this like, is it starting to like
Yeah. I mean,
mesh
yes,
in our
yeah,
brains
okay.
a little bit?
Maybe after 1 or 2 problems.
Yeah, let's do another one. I feel like Fisher's is the one where we should work on more. Because this is the one where like it's so easy to go wrong. Okay, so first of all, there is no most oxidized carbon. So for this one, it doesn't really matter which one's on top. Yes,
What we just did, I know we're moving on, but like that's it. It's like going from a line.
that is it. That is it.
A line and go to a fissure.
Yes,
Okay.
that is it. That's
It
what
doesn't matter how you draw it on each side, or is it just the lines?
it just. All right. So the basis of a fissure is a line down the middle, and the lines across, each representing one of the carbons
Got
that
it.
go across. You want the most oxidized carbon always on top. Let me add that in actually real quick.
So is the final answer that we write on the test the one in the middle, or?
Yes, yes. Don't worry about this.
Okay.
Questions, comments? All right, moving on. Oh, there's a bug.
Why
Not
you
going-
zip your bag so it won't go
I don't know, okay? All right, we're throwing away this piece of paper.
You are so cute. Oh my goodness.
Oh my goodness.
Okay, next question. All right. So I'm going to choose a carbon to turn, I'm going to make this carbon red. Actually, no, I'm going to do this one. Might as well. Okay. I'm going to make this carbon red. I'm going to make red carbon my top carbon. Okay. I have 2 carbons on the end, 3 carbons in the middle. 1, 2, 3. Okay. Carbon on top is going to be red carbon. Red carbon. Okay. Both of them are CH3s on the end, so it doesn't really matter. CH3, CH3. Right now I have CH3s on the top and the bottom, so it doesn't matter. I'm going to put CH3 red on top. Okay. So, on this one, the middle carbon is easy. They're both hydrogens. It really doesn't matter, right? But for our little purposes, I'm going to draw them in. H1, H2. Okay, that'll help us a little bit. All right, so in this one, our perspective is going to be a little bit different because guess which way I'm going to be standing? I'm going to be standing this way because I need to have my top carbon on this side, the furthest away from me, right? Because it needs to be on top. Right? When I look down, the carbon needs to be on top. Right? So do you notice how when I'm looking down, I'm looking a different way?
Yeah.
Right? The pointing for, oh, I should draw right in my numbers. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. Okay, so for carbon 2, do I look down or up? I look from the top down. From top down, okay? From top down is my alcohol on my left or my right? Left or right? My alcohol is going to be on my left or my right?
Right?
I'm looking top down. This is the paper. Alcohol left or right? Left or right?
Is the left out of the paper?
Left is going to be out of the page because here's the paper and I'm looking this way.
So left.
Left, okay. So alcohol is going to be left, which means hydrogen is right. Okay.
So quick question. So
Yes.
like in the previous example, our first carbon was starting from the right side, so you were looking from here. And then in this carbon, we are starting from here,
Mhm.
so we are looking from here. So that's why your hand is like this.
Yes.
Like in this one, we started here, so we were looking from this. You were starting.
Yeah, my perspective changes,
Changes.
right?
Okay.
Because always my most oxidized carbon or the carbon on top needs to be on top when I look.
So since for this one, both were like equally CH3, it doesn't matter if I start from here or here. How do you know that?
It
that
usually
is the
doesn't. Usually on a test, they will put a carboxylic acid or a ketone or something so that it will be the most oxidized carbon. This one, I did it this way because I'm using the same thing for isomers. Oh, we didn't even do RNS or isomers. We can do that later, don't worry about it. But yeah, so the reason why I made this one this way is because I'm reusing the same structure for other stuff, so it looks a little boring. Don't worry, they'll spice it up for you. But okay, so carbon 2, all right? Looking at it this way, but I'm looking at it from the bottom. When I look at it like this, hydrogen 1, right or left?
Right. H1 right.
Right. Hydrogen 1, right or left? Right.
Right.
Right, because it is facing out of the page. Hydrogen 2 is left. He's facing into the page. Hydrogen 1 is right. Hydrogen 2 is left.
And you were looking at it that way because when you did the first one, you were looking down or up?
I was looking down from the top down
When you did the first carbon.
for carbon 2.
For carbon 2, you were looking down.
Yes, I was looking down. I was looking this way. Which means that for carbon 3, I need to switch my perspective
Okay.
and look this way.
Okay.
Remember, I always look, my perspective is with the direction of the point. pointing up, that means I look from top.
Okay.
Okay, so here's a little trick that'll help you guys. Remember, I alternate my perspectives, right?
Yeah.
So here,
No, you don't come in here.
right? I alternate my perspectives every carbon, which means that my perspective for this carbon and this carbon must be the same, right? Carbon 1 and carbon 3 must have the same perspective, which means that right and left on those carbons,
And that would be orange.
yes, there will be the same. So I don't have to redo the dumb looking thing, I just have to do this. Okay? If my perspective is the same, the right-left rule will be the same.
Okay, so if the carbon's pointing up, you're looking down.
Questions, comments about fissures? I know this is very, very weird. Bear with me, bear with this. I don't think fissures come up again, unless you're on the final, but. So this is just one of those things, learn, get through. I know it's weird, but you just gotta do it, work with it. Questions, comments? Do y'all wanna do another one?
Yes.
Yes, alright. Let's do one more, okay. So, this one, I have a carboxylic acid, so our job is easy. No, not easy, but we know where our carboxylic acid is gonna be.
I have a question. So do we have to do like a nomenclatures like in a Fisher structure form?
What do you mean by that?
Like can they give us like a Fisher structure and then we have to do like a nomenclature
Like
a
naming?
R, S, yeah, the naming. Like a
R and S you can do on this. Naming is a little, naming.
have you seen in any past?
I don't-
or no?
Usually if they have you name a line angle.
Okay.
That said, you never know, so. But if they give you a fissure and told you to name it, that would be an interesting thing to do.
And that's what I was like. Will they give it or not? 'Cause
I've never seen that before, but who
Line angle
knows?
or a Newman, because we had a Newman on.
Newmans will be ridiculously hard to name.
Well, they gave us one on the quiz.
Name a Newman? Okay, so if they have you do a fissure or a Newman and they ask you to name it, this is the part where you convert it back to a line angle.
Yeah.
Yeah.
Convert back to line angle
That
so it
name
makes
it.
a little more sense.
Yeah.
It's easier to name line angle.
Mhm.
Good place, alright?
Yeah.
R and S you can do, it's a little easier, okay?
Okay.
Okay, so COH, I have CH, oh no, it's the wrong color. Okay, so I'm gonna name my number of my carbons, 1,
So see you at
2,
one.
3, 4, 5, 1, 2, 3, 4, 5. Okay. CH3. Okay, so my first carbon, I have 2 hydrogens, H1, H2. Okay, H1, I'm not gonna go up there, I want y'all to think. H1, right or left?
See, how do we know whether we're going this way or this way?
That's where I'm kind of stuck.
Because I see the COOH, right?
Mm-hmm.
And I know that I'm looking down at this carbon, but I don't know if I'm looking from this side or this side.
Well, we're gonna look from the side that puts my carboxylic acid on top. So which way puts my carboxylic acid on top?
Right?
So am I looking this way or this way?
So for carboxylic acid, we'll be looking like from this way, right?
I'm gonna look this way,
Okay.
right? Because when I look this way, my carboxylic acid ends up on the furthest away from me, which means it's on top,
There we go. Okay. Now it's making sense.
right? So basically all I have to do is just like rotate this entire graph 90 degrees.
So H1 is out of the page, so on the right, since our carboxylic acid is in the front, or the top. Furthest
Perfect.
away from us.
Did everyone understand why H1 is on the right?
Yeah.
Okay, I'm gonna rotate this 90 degrees. Rotate this 90 degrees, so carboxylic acid's on top. That way, hydrogen 1 is gonna be on my right, because it's out of the page.
Makes sense.
Make sense?
Right.
Okay. So, here's another pro tip. So, I automatically can do carbon 4 because I know carbon 4 is going to be the same as carbon 2, right? So carbon 2 is going to be iodine, it's going to be on the same side as H1. Hydrogen is going to be here. You want to hear another trick?
Yeah.
This is going to make your lives way easier. Remember, carbon 3 is the reverse of carbon 2 and 4. So now I can just switch, right?
Yeah.
So hydrogen 2 is facing in, chlorine is facing in. Since I switch, my chlorine is going to be on the opposite side. Okay? So let me draw that out, okay? So I only really need to do this weird visualization thing once. I only need to do it once. And then I know that every other is going to be the same, and then the one in the one that's next to is going to be flipped.
Perfect.
Does that help at all? Does it make sense? Questions, comments, rude remarks? Please no rude remarks, but you know. Does this
I'm
make
still trying to, I guess, know the in and out.
It is really odd. I will highly suggest practicing. Talk to your professor. They might have a better way of doing this. This is the way I've learned it, but there's always new ways of doing things. So they might have a better idea. Come in for tutoring. Then you can like actually practice a lot more. But yeah, so I know it's really weird. Come in for more help. I tutor from like 10 to 1 on Wednesdays. So come in for that if y'all want more help on this. But yes, so that's Fisher. I'm going to move on so we can talk about constitutional isomers and enantiomers and diastereomers. And then we're going to come back. Hopefully we'll have a little more time so we can do more questions that y'all are curious about. But I want to make sure we're covering everything. No. Okay. Question 4. So what we're going to do is a constitutional isomer and an enantiomer and a diastereomer. A constitutional isomer. What is a constitutional isomer?
Having same number of carbon and hydrogen.
Yeah, so basically what it means either the same chemical formula. And what we mean by same chemical formula is literally the only requirement is that I have the same number of atoms. I can do whatever I want from then on. Okay? As long as it doesn't become an enantiomer or a diastereomer. I can do whatever I want. Basically, I have the same atoms, but I can bond it differently. So, a constitutional isomer, for this one, I can just bond differently. So,
Can a molecule be a constitutional and a same molecule as well? Like in the
yes.
quiz,
Um,
there was a constitutional, so I wrote constitutional, but he said the professor said the better answer is the same.
yes, so you always want to say the more accurate one, right? Anything can be a constitutional isomer, but there can only be so many. There's only one same, so you have to say same and
like
same.
this one.
Yeah, those are the same.
So this one, so these are the same,
Yes.
even though they have the same carbon.
It is a constitutional isomer, but it is more specifically the same. All enantiomers are constitutional isomers, right? Because they all, in order to be a mirror image, you have to have the same chemical formula. But I'm going to say enantiomer on my test because enantiomer is the more accurate one. So for example, on the original one where I was like, is the enantiomer the same? Is it an enantiomer? Yes, technically it's a mirror image. But it's not an enantiomer because I have superimposable, so I'm going to say the same. So you see how something can be one thing but also the other thing? Think of it as a Venn diagram, right? I have a giant Okay. I have a giant circle and it's constitutional. Alright? And within that I have same. I have enantiomer and I have no, actually no, diastereomer is the same as, okay. And then I have diastereomer, and then I have enantiomer. So I have like within, well actually, yeah, so like, it's like a Venn diagram. Okay, I just have like little, like I have a lot of different types of things, but like an enantiomer is a constitutional isomer. But just because I'm a constitutional isomer doesn't mean I'm an enantiomer. So when I choose the thing I put on my answer, I want to be as specific as possible. Okay, so constitutional isomer mean I have the same chemical formula, but I can literally do whatever I want. So how about for this one, I'm going to move this CH3 over to the end like this, and then I'm going to move the alcohol to the end, and I get this. And then I can move my bromine too. So I have 1, 2, 3, 4, 5, 6 carbons. 1, 2, 3, 4, 5. No, I'm missing a carbon. Always count your carbons, by the way. 1, 2, 3, 4, 5. And then let's say I want to put my bromine here. I have the same chemical formula, but I've made a completely different looking molecule. I have the same chemical formula, but I have a completely different looking molecule, and that means I'm a constitutional isomer. Same chemical formula, but it can be bonded completely different. It doesn't matter at all. Okay? So now let's talk about enantiomer.
Hey, let me ask you.
Yes.
Does that bromine? Okay, let's say they give us 2 of them, right?
Yeah.
So they give us, this is gonna be constitution. So let's say on the second one, the bromine was a fluorine. So it's a different halogen.
So do I have the same chemical formula?
No.
No. So is it going to be a constitutional isomer?
No.
No. It's not going to be any of them. It's going to be a different one. So I think on the test I took, they have like all these options, and there's like different or like completely different. You'd select different.
Okay.
Okay, so enantiomer means non-superimposable mirror image, or let me do some erasing real quick.
So
Okay,
you change the number of the bromine. The bromine is not by the COH.
yeah,
It's
I
by
moved it.
OH.
It doesn't matter.
It doesn't matter.
It doesn't matter. I can literally do whatever I want. As long as I have the same chemical formula, which I have. All right, so non-superimposable image. I'm going to do my little mirror thingy, and then let's see. It's really ugly. Hold on. This is what we call the enantiomer. Do I have exactly the same molecule? No, I have a completely unique, it's a different molecule, right? So this mirror image will not come back on top of this one. It's non-superimposable. Does it make sense?
The superimposable, what's the name of it? It's not called mirror, right? It's
If it's superimposable, it means I get the same thing.
same, okay.
If I take the mirror image and it can go back on top, it's the same thing. Enantiomer is when I take the mirror image and they're different. For example, if I had a right glove and a left glove, they're mirror images, but they are not the same thing.
Right.
If I took the right glove and a right glove, I would, you know what I mean? Yeah. So,
If it's both right, then it's the same thing. But if
yes.
it's right and left, then it's a mirror.
Yes. Enantiomers, actually, okay, I have a cool story about enantiomers later. Okay, but does this make sense? All right, cool. Diastereomers. So, we didn't get to this, but basically, how many different chiral carbons do I have?
is one by the COH.
Okay.
COH bromine, one here. And then
This stuff I'll just.
Is this one chiral?
no,
No, it's not.
Is this one chiral?
no.
No.
Is it? Yes or no? You all say no, but I say yes.
But it's connected to one CH3 and then it's connected to OH, one carbon, and then H, yes. 4 different things.
They're different. Look, I have carbons, yes, I've got carbons, but look at what this carbon's attached to and what this carbon's attached to. They're different.
Oh, I see.
You can't just look at the ones it's directly next to, you have to keep going.
So that is a chiral.
They have to be exactly the same. So this one is chiral. Does that make sense?
Yeah.
How about this one? Is it chiral?
No. Yes.
I think it's chiral.
You think it's chiral?
Yeah.
I think so.
Yes.
Yes.
Yes. Are y'all just joining the bandwagon? No? So y'all think it's chiral?
I do
It's
think
chiral.
so.
Y'all think it's chiral?
You said don't look at what's attached to, right? So don't look outside,
Look beyond.
beyond basically.
And so when I look beyond, what do I see?
Yeah, we
There
have
is-
OH on the
yeah.
side,
We have
and we have
CH3.
Yes,
Yeah.
right.
Yeah.
Yes, so if I had
hydrogen.
this, would it be chiral? If I had another?
No.
Not the same thing. 2 same thing.
But here I have another hydrogen, what's attached here?
Carbon.
Carbon, so it would still be chiral,
Okay.
right? In order for this to be achiral, in order for this carbon to be achiral, I literally have to have this entire thing on the other side. Because then they will be the same thing.
So how
So like
far
this way.
are you gonna look to make it chiral or not? So you know how you said you need
As
to
far as it takes,
Oh,
So how fast it takes?
yes. So for example, this carbon, chiral or achiral?
Yeah, chiral.
Achiral.
Is that
Chiral or achiral?
chiral?
Chiral. Does that make sense?
Sit down one more time. The
Okay.
last you said chiral, okay?
Chiral or achiral?
That's chiral, yes. Chiral.
Chiral? Is this the exact same thing as this thing?
Oh yes.
Yes, so
Chiral.
it's achiral, because both things are the same. Chiral or achiral?
Chiral.
It is chiral, because look, I added something, so now one side is not the same as the other side.
I thought you said chiral is 4 different things attached to it.
Yes, so this
the
thing
one is the
is
same.
different from this thing now.
No, I mean minus the.
Yeah, so
Chiral.
without this, it is the same. With
it's not
this,
chiral then.
with this, it is chiral.
Oh, so with that is chiral.
When I add the,
that,
yes,
it's
when I add the extra methyl, it's chiral.
Yes.
Without the extra
It's
methyl,
not.
it is achiral. Yes.
Okay.
Does it make sense?
Yeah.
Perfect. Okay, let's go backwards. Okay, so this carbon is chiral. Okay, so I have 3 chiral centers. A diastereomer means that I am bonded the same way, but my chirality has changed in at least one. So in order to get a diastereomer, all I have to do is change the chirality of 1 chiral carbon. Okay? So, okay? So, all I have to do is change the chirality of 1. So I'm going to do, and what I can do by changing chirality is literally change this from out of the page to into the page or vice versa. Okay? So I can change any of these to in or out of the page, and I would get a diastereomer. Okay? So what do y'all want to change? Up to y'all.
OH.
OH, y'all want to change OH? Okay, cool. So currently it's on a wedge, I'm going to switch it to a dash. This is what we call diastereomer.
okay, so we saw this one, the one from the paper, and then the one you just drew. Simply because that OH,
Change chiralities. It's not an enantiomer because it's not a mirror image.
right,
So it's a more general, like, but everything's bonded the same way. So I believe if you look in your lecture note, there should be a slide where it has like a little chart thingy that looks kind of like this. Look at that slide, it'll explain this very, very well. So it'll explain like how the branching works and like if it's constitutional, if it's this, if it's that. That's very, very helpful. So
Dr. Thomas said that the diastereomer, it has one just a bonded cis and trans, then a cyclic cis and trans, and then I think the RNS.
yes, so that's geometric diastereomer, so that means I switch on the double bond. I don't have it here, but yes, that's geometric diastereomer. This is RNS diastereomer, right? Because here, this is not double bond, I'm just changing RNS, right? When I switch from dash to wedge, I change RNS.
Okay. Makes sense.
Questions, comments? I know this is like really, really weird, really complicated. Believe me, like diastereomers, enantiomers, like chirality is one of the toughest things for me when I went through Chem 1. So feel free to ask questions. We have a couple more minutes. If you want to do another problem, maybe talk about fissures, talk about something. Yeah, questions, comments?
Can we do?
Go ahead.
I was just thinking if we can do one more example of like the same enantiomer, not enantiomer, the diastereomer.
Okay, perfect. Yeah, let's do that. This one's a little simple. Let's do this one. Okay, so I'm going to start with an enantiomer because I can get a mirror image a little easier. So I'm going to make enantiomers red on this slide. Okay, so I'm going to get my mirror, and then I'm going to do enantiomer. All right, so all I have to do is literally take the same thing. And this is my enantiomer.
And in order to make it the dye one is just I have to change, for example, if I change the iodine to a dash.
Yes,
So now it's
that's a diastereomer. Okay, so let's do our diastereomer next. No, come back. Okay, purple. Let's do purple for diastereomer. Okay, so diastereomer, yes, all I have to do is change one to a different thing. So I'm going to change this. And now I have a diastereomer. Diastereomer. Right, I just changed chirality of one carbon and I get a diastereomer. Okay. And now I'm going to do constitutional isomer, and this one's the fun one. So let's do blue. I like blue. My constitutional isomer is going to be blue. All right, so now I am going to do some reconstruction. Let me do this. This is a constitutional isomer. I have the same chemical formula, but I have a different bonding. Completely different bonding. The only requirement for constitutional isomer is same chemical formula, which I have here. So, if they let you choose constitutional isomers, be creative, it's fun. Have some fun.
So in the past exam, do you have to I know some past paper you just have to circle out the best one. So do they make you also draw sometimes?
It depends. I actually didn't take regular OChem, so I'm not quite sure, but it just depends. Yeah,
What is regular okay?
the one you're in.
What did you say?
I took it. Yeah, I took a different version, but
Yeah.
Wait, what did you do?
I took a different version of the class.
Oh.
Questions, comments? Any question about the things we've done? We have we're on time, but questions, comments before we go. I know this is really complicated, so come in for help, please. Don't do this by yourself. Come in for help. We are more than happy to help. We are open. I have a slide. From 10 to 7 on Mondays to Thursdays and 10 to 4 on Fridays. We're in the basement of the library. Come on in for help.